5 and I get 0 over 0. So then I have limit as x approaches 5. And I already know the trick now, and I cannot forget that, right? I know there must be a factor of x minus 5, top and bottom. Right? We agree? Okay, so then what do I have here?
X minus 3.
I have x minus 3, and here I have
X plus 2.
x plus 2. Do we agree? Okay, these two go away because remember, I cannot simplify unless I write x not equal 5. But that's redundant. When I say x approaches 5, I mean not 5. So I don't have to state that restriction before I simplify. Otherwise, I have to. See, when I divide x over x, I cannot write 1. I have to say it's 1 only if x is not 0. So when I simplify by x minus 5, I have to state the restriction somewhere, x is not 5. But it's redundant in this case because this clearly specifies x is not 5. So there is no need for this. But here there is a need for this. Okay, so then now I have x minus 3 over x plus 2. I plug in 5 again. The limit operator goes away. So I have 5 minus 3, which is 2. And I have 5 plus 2, which is 7. And it's done. Are we in agreement with this? Everyone? Okay, now the second one is from the right-hand side. So when I plug in 3, I have to plug in 3. I get 4 over 0. And I know that there are 3 possibilities, but I have to choose one. So one possibility is positive infinity. The other one is negative infinity. And the last one is DNE. But since it's from one side, chances are that the answer is either positive infinity or negative infinity, not DNE. Chances are. So 3 from the right-hand side is 3.1. The denominator is positive. The numerator is positive. So the answer is infinity. Not this and not this. Okay, for this one, when I plug in 0, I see that I have 0 at the top and I have 0 at the bottom. So again, I have a situation like this. But this is a totally different type of limit. I cannot factor. Maybe I could later on, but right now I can factor. So it's not like this. It requires me to do what? Rationalize. So I will multiply top and bottom by Are you with me on this, everyone? Yes? Okay. So now the numerator, I cannot drop the limit operator. So the numerator is h multiplied by the square root of h plus 3 plus the square root of 3 divided by this I have to perform. I multiply these two. A minus b, a plus b. This is our first agreement, right? A plus b times a minus b is a squared minus b squared. A squared minus b squared. Any questions? It's not okay to simplify like this. I have to write it one more time. So this is limit as h approaches 0 from h, the square root of h plus 3 plus the square root of 3 divided by h. Now I'm allowed to simplify, and if you consider 0 here, I didn't say you did, but I'm just saying careful, write 1. Now you can drop the limit operator because we are ready to plug in 0. So the square root of 3 plus the square root of 3 is an apple plus an apple, which means 2 apples. On the last one, I'm asked to find the limit from either side of f of x. Okay, which means I have to find 2 limits. I have to find the limit as x approaches 2 from the right, 2 from the right from this function. And I have to determine limit as x approaches 2 from the left, 2 from the left from this function. Both linear functions, plug it in, it's done. 8 minus 3 is 5. 4 plus 1 is 5. The answer must be 5. So limit from either side of the function f of x is 5. Any questions? Any questions? Okay, very good. So let's go back to maybe I should put it here. I should scan it for you. Okay, let's go back to this handout. we talked about everything here except a theorem that I want to start with today. Okay, so let's just browse through. We say that f of x is continuous at a if this happens, which means the limit from the left, the limit from the right, and the function value are all equal. We had that in our notes last time. In other words, f of a exists, a is in the domain, so the function has to be defined there, otherwise f of a will not exist. The limit from the left, the limit from the right both exist, and f of a and the limit are all equal. All these three are in here. A, B, and C are in this little information that I have, which is not little at all. Okay, so this implies A, implies B, and implies C. And we also talked about limit from the left-hand side equals the function value. We say that the function is continuous from the left. Now let's see, what will you tell me to put in here? If the limit from the right of f of x equals the function value, then we say that the function is, what will you tell me to write? Very good. Continuous from the right. Indeed. And a discontinuity is removable, as we discussed last time. It happens when both sides are the same, but they don't equal the function value, or the function is not defined there. Okay. And we talked about infinite, jump, and removable discontinuities. And we looked at a function last time in which we were given two parameters, two unknowns, and we were asked to make it continuous everywhere. So we're going to look at another problem right now, part B, but I want to go through this theorem, which I stated, but I did not write it. If f and g are continuous at a and c is a constant, then the following functions are continuous. All I said last time is that any combination of continuous functions is continuous. So if f and g are continuous, f plus g is continuous. Their sum will be continuous. Their difference will be continuous. Their product will be continuous. Their ratio will be continuous, of course, when g is not 0. And a number times a function will be continuous if the function is continuous. I did state this theorem, and I wrote it a couple of times for polynomial. Any polynomial is continuous on all real numbers, and any rational function is continuous wherever it's defined. Also, root functions, trig functions are continuous everywhere they are, or whenever they are defined. So I would like to look at another problem like the one we looked at last time. And then I would like to explain the intermediate value theorem. It's a very important theorem, and we will be using it again in chapter 4 when we will be able to solve, I know it's mind-boggling, we will be able to solve by hand any equation, including this one, and find this solution by hand with no maple, no calculator, nothing. So we will learn how to do that in chapter 4. And this is part of that condition. If we don't understand this and we're not able to apply it, we'll have difficulties in chapter 4. So it's called the intermediate value theorem. So I would like to look at this problem, and you will tell me what we need to do. So we have a function g of x, which is defined as a piecewise defined function. It's a piecewise defined function, cx plus 1 if x is less than or equal to 3, and cx squared minus 1 if x is greater than 3. So we're asked to find c such that the function g is continuous everywhere. So the first thing I have to write is, can anyone tell me what function is this? Very good. Linear. A constant times x plus 1. Polynomial, but linear. Very good. Excellent. Can anyone tell us what function is this? Quadratic. So polynomial. So what will I say about cx plus 1 on the interval -infinity to 3. Notice that I did not include 3. And what will I say about cx squared minus 1 on the interval 3 to infinity? And definitely I'm quoting this theorem. Yes, absolutely continuous as a Pauli function. Cx plus 1 is continuous as a polynomial function, and cx squared minus 1 is continuous as a polynomial function on the interval. Now, what could be the problem? Continuity, exactly. Continuity at x equals 3. Perfect. Good. What has to happen at x equals 3 for this function to be continuous? Okay, equal. The explanation is equal. No.
X approaches 3 to the left. Cx plus 1.
Yes, to the left is cx plus 1.
Must equal the x approach 3 to the right. Cx squared must equal to g of 3. Or
Very good. And we'll find those 3 in a moment. Excellent. This is the definition of continuity at a point, and this is like something that we cannot forget. This is absolutely very important here. Okay, so now can anyone tell us the limit of this?
C3 plus 1.
3c plus 1. Very good. Can anyone tell us the limit of this? Very good, excellent. And can anyone tell us g of 3? And tell me which one do you use? Because you cannot use both branches. You have to specifically use which one. Very good. So what will that equal to?
3c.
Very good. So now, obviously, this must equal this. So 3c plus 1 must equal 9c minus 1. Let's say I'm moving 9, I'm moving -1 to the other side. When I move 9, I get -6c. And when I move 1, I get -2. So therefore, c must be 1/3. That was not a difficult situation. I didn't have to solve a system. I only had one variable, and the equation was a linear equation. So now, can anyone dictate the function that is guaranteed to be continuous everywhere? What will you say?
Cx plus 1 will be continuous at infinity.
We just determined c. We need to put it back in, right? So 1/3 x plus 1 and
1/3 x squared.
can I say that is continuous on this? Is it guaranteed?
Yeah.
Of course. We made it. We determined the constant such that the function is continuous at 3. The rest was continuous because the function was made up of polynomial functions. And those are continuous everywhere. But now, because we stated the continuity at the point, we came up with an equation that allowed us to determine c by solving it. And now it's guaranteed that this function is continuous everywhere. Very good. Now, I would like to talk about the intermediate value theorem. Any questions? Any questions? Okay, IVT, intermediate value theorem. Intermediate value theorem. First condition, function must be continuous. Is continuous. On an interval, let's say a comma b. Number 2, second condition. Function must change sign on a comma b. What are the options? Either f of a is greater than 0 and f of b is less than 0. That's one option. What is the other option? F of a less than 0 and f of b. Very good. That's what I mean by function must change sign. So imagine an interval a comma b, and the function either does this, negative to positive, or it does this, positive to negative. These are the two options. Then what must happen if that's the case? If a function is continuous on an interval and it changes sign on that interval, what must happen? What do you think? It's okay if you're wrong. So I have a continuous function. Okay, let me draw it. So let's say this is a and b. And let's say this is the function. In my example, f of a is negative and f of b is positive. So what must happen if that's the case? Continuous function and changing sign on an interval. Right, so what must happen? If it's continuous and it goes from negative to positive, or it goes from positive to negative? Exactly. It must be 0 somewhere. If it's continuous, that's crucial. If it's not continuous, it doesn't have to cross the x-axis. But if the function is continuous and it changes sign, how can a continuous function go from negative to positive if it doesn't cross the x-axis, or vice versa? If it's continuous and it comes from positive and goes negative, it has to cross the x-axis. Okay, so you may or may not like this. And there exists C in the interval a comma b such that f of c is
0.
exactly. That's the intermediate value theorem. And now you can say, okay, nice. But when do I use it? Here's when I use it. Here's an example. Let's suppose I want to solve this equation. X squared equals the square root of x plus 1. Or even more difficult, cosine x equals x. Okay? And I am told, show the intermediate value theorem, I have to say, is not powerful to the extent in which it will tell us the solution. No. It would only say there is a solution there. Between 1 and 2, this equation has a solution, or this function has a 0, for sure. But it will not say, okay, here it is. No. We have to wait in chapter 4 to determine it. But we will be using this. So we are told in this problem that there is a solution between 1 and 2. In other words, we are told actually use the intermediate value theorem to show that there is a solution. Here's my first step. This is problem 1. I will create a function by setting the equation equal to 0. Okay, so here's my function, which is f of x equals x squared minus the square root of x plus 1. Question. In order to use the intermediate value theorem, I have to show two things. What is the first thing I have to show? that the function is continuous. Okay, so I'm coming back here. Root functions, trig functions, polynomial functions, rational functions are always continuous where they are defined. So I'm going to state that theorem. I'm going to say f of x blah 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 is a continuous function as a difference of two continuous functions. Definitely on 1, 2. X squared is polynomial, continuous everywhere. Now the square root of x plus 1 in the interval 1, 2, the square root of 2, the square root of 3, definitely continuous where it's defined. So the first part of the theorem is clear. The function is continuous. Now what is the second part without which I cannot conclude that there is a solution between 1 and 2? What do I have to do now? Find exactly, and find f of 2. What has to happen now? What if they're both positive? Is there a solution between 1 and 2? No. What if they're both negative? Is there a solution between 1 and 2? No, because the continuous function doesn't have to go. And by the way, the interval should be a 1-unit interval. You can't really say, okay, there is a solution between 0 and 100. No. You have to be very close, or as close as possible. You have to say between 5 and 6, between -3 and -2, between 0 and 1. It's 1-unit interval. We prefer even smaller, but 1-unit interval minimum. Okay, so I plug in 1 minus the square root of 2. This is a negative number. That's all I need to know. I plug in 2. 4 minus the square root of 3. This is a positive number. That's all I need to know. I don't really need the number. I just need to verify that it's indeed negative or positive or the other way around. And what do I conclude then? From A and B, I conclude what? There exists a C in the interval 1, 2 such that f of C is definitely 0 by IVT. By IVT. By the intermediate value theorem. Continuous, changes sign, we must cross the x-axis. However, as I said, the intermediate value theorem will not help us determine the solution. It will only give us a unit interval in which it's guaranteed the solution to be, but it will not determine the solution for us. Okay, now I want to draw your attention to one thing that when you read, I'm hoping you're reading the text, you're going to see that the general intermediate value theorem, it says something different. It's the same thing. This is the application, the straightforward. This is something like this. Suppose that a function is continuous on the interval a comma b, and let n be a number between f of a and f of b, which is, in my case, is 0, right, is the x-axis. Then there exists a number c in the interval a comma b such that f of c is n. So for simplicity, I went directly to the application by replacing n by 0. And that's all it means. Okay? So suppose that f is continuous on the interval a comma b, and f of a is a negative number, f of b is positive in this example, or in this situation, and there is a number c in the interval a comma b such that f of c is 0. So I went directly to the application, because I'm not going to test you on the theorem. I'm going to test you on the application of the theorem. So I just don't want you to think that I did anything fancy there. Not fancy at all. Okay, any questions? Would you like to work on another problem? Okay, very good. So we are trying to show that there is a solution and the problem was giving us, normally we are not given the interval. We have to find it. We have to find the interval. So we are given in this case 0, 1. So we are asked to show whether this equation has a solution between 0 and 1. How do I start? What is my first step? Yes, create a function. So cosine x minus x equals 0. So therefore, what is our f of x? Good. Number 1, or part A, what do I have to say? And again, I'm quoting the same theorem over and over. Trigonometric functions are continuous wherever they are defined. And any combo, if f and g are continuous, the following functions, the sum, the difference, product, ratio, and the constant times the function, they're all continuous. So, f of x is continuous, at least on 0, 1. It's continuous everywhere. But continuous on 0, 1 as, these should be closed if I left them. Yeah, I mean c is in 1, yes. So at least on the interval, continuous on the closed interval as a combo or difference, maybe it's better, difference of two continuous functions. Good. Part B. What do I have to show in part B? F of 0, yes, and then f of 1. So f of 0 will be cosine 0 minus 0, and this is cosine 1, which means not 1, but 1 radian, not 1 degree, that's what I meant, minus 1. Okay, how much is cosine 0? Yes, indeed. How much is 1 minus 0? Good, that's all I care about. It's greater than 0. How much is cosine 1? 1 radian means roughly 60 degrees. Is this number smaller or bigger than 1? Remember we talked about it in squeezing theorem. Cosine cannot be more than 1. It cannot be less than -1. So this is a number definitely smaller than 1. A number less than 1, not negative, because 1 is in 1 radian in the first quadrant. So this minus 1. Negative or positive? What do we conclude from A and B? From part A and part B, by IVT, what do we conclude? Yes. There exists a C in the open interval, so the continuity is on the closed, but yes, such that f of C is definitely 0. In plain English, it's guaranteed if both conditions are fulfilled, function continuous and changes sign. It's guaranteed by the intermediate value theorem for the equation or the function to have a solution or a 0 respectively in the interval 0, 1. Any questions? Any questions? Okay. Let's continue. We already did this. I did it with you when we looked at all sorts of functions. That's the next section, which is limits at infinity and horizontal asymptotes. We already talked about this. So let's go ahead and refresh our memory. And then look at work and problems. Okay. We already know that if we determine the limit as x approaches infinity from a function, so that's section 2.6. Did I give you an answer? You have, okay. 2.6, limits at infinity. And of course, that goes with horizontal asymptotes. If I know, let's say, that limit of as x approaches to, infinity, of f of x is 2, I already know that y equals 2 must be a horizontal asymptote. We know that. And that's what this says. The line y equals L is called the horizontal asymptote of the curve if the limit of f of x as x approaches negative infinity is that number, or the limit as x approaches infinity of the function is that number. So now I wanted to refresh your memory again on these three functions. Arctangent, if you remember, we graphed arctangent, and I said, please remember this graph. I already put your horizontal asymptotes there. And here's the graph of arctangent. Very important to remember this. Y equals arctangent x. And now I will ask you, what is the limit of as x approaches infinity from arctangent x? And what is the limit as x approaches negative infinity from arctangent x? Of course. When we say pi over 2, we know it's radian. If I say 5, then I have to say radians. But if it has pi in it, it's very clear. But it's not a mistake to say pi over 2 radians. But it's okay. And then the other one, which means this and this are horizontal asymptotes. That was one. A refresher. Please go back to the previous handout with all those graphs. So that was the answer here. Now we want to graph e to the x. Does anyone remember how to graph e to the x? Exponential function, increasing on all its domain, crossing at 0, 1. Here it is. This is e to the x. And we're asked to find the limit of e to the x as x approaches negative infinity. And the limit of e to the x as x approaches infinity. Okay, what would you say?
0.
Very good, which means y equals 0 is what? Very good, excellent. And what about the second one? Which does not make it a horizontal asymptote. Very good. So this function has a horizontal asymptote only at one end. Okay, here it is. And now let's look at natural log. Does anyone remember how to graph natural log? Here it is. It's the inverse of this function. Okay. So this is natural log, and we want two things again. We want limit of natural log x as x approaches infinity. And we want limit of f of x as x approaches 0 from the right. Right, which does not mean that the function has a horizontal asymptote. And the other one, negative infinity, which means that x equals 0 is a vertical asymptote.
What's that say? When you write y equals 0, what's that say? Y equals 0.
A horizontal asymptote. In other words, it's a horizontal line that the function will eventually approach as x approaches infinity, negative infinity. Okay. Last thing before we look at problems here, the theorem. Let's see if we understand the theorem. So R is a rational number and it's a positive number. So this is the exponent here. So I'm talking about limit as x approaches infinity from 1 over x to the r, and r is a positive number. So if r is a positive number, just imagine x squared. Let's say x squared. When x approaches infinity, where does x squared go? Let me give you the example. Let's say it's x squared, because it's a positive number. R is the power is a positive number. So as x approaches infinity, where does this go? Good. Where does 1 over infinity go? Very good. It goes to 0, which means y equals 0 is a horizontal asymptote. Now, what about the other way? When if x to the r is defined for all x, of course, and then we have x raised to negative infinity. When x approaches infinity from x to the r. So let's say limit as x approaches negative infinity from 1 over x to the third. R is still a positive number. So let's say now, where does x to the third go? Good. Where does 1 over negative infinity go? Exactly. So y equals a horizontal asymptote. Notice one thing, that we checked infinity and negative infinity. So I'm going to say at infinity, at negative infinity. Not all functions have the same horizontal asymptote. Let me give you a numerical example. I should say a graph, better. Okay, so let's suppose I have this graph, which is very possible. Right? And we had, I don't even need to give you another example. We already had one. This is a horizontal asymptote only at infinity, not at negative infinity. And this is a horizontal asymptote only at negative infinity, not at positive infinity. So yes, we can have a graph that does this. It's very possible. So the horizontal asymptote, I'm going to put a number in here. Let's say y equals 3. Horizontal asymptote is y equals 3 as x approaches infinity. But it's y equals negative 3 as x approaches negative infinity. As x approaches negative infinity, function values get closer and closer to negative 3. So a function doesn't have to have the same horizontal asymptote. On page 140, 141. Let's look at problems 15 through 38. Feel free to choose. 15 through 38. Any problem you would like to look at? Which one? 27. We have limit as x approaches infinity from the square root of x squared plus ax minus the square root of x squared plus bx. Okay. I'm asked to determine this limit if it exists. We're going to start a list of indeterminate cases. Okay, so I'll come back in a second. So list of 7 indeterminate cases. The first indeterminate case that we already saw is 0 divided by 0. That's our first one. Slowly but surely, we're going to get through all 7. Okay, so I'm coming back here. So list of indeterminate cases, not undefined, indeterminate, 0 over 0. In one example that we had on our quiz, nobody can conclude anything about 0 over 0. So initially the 0 over 0 in our case, it turned into what? 2 over 7. Who would have known? No one. Indeterminate case. Okay? 0 over 0. Nobody knows what to expect. Indeterminate case. Okay, very good. So coming back here, what is the first thing I need to do when I'm asked to find a limit if it exists? It's all the same. The first step is all the same anywhere in any case. What is it? That's true. You already plugged it in, right? That's what you did. Okay, that's all I wanted anyone to say. So this approaches when x approaches infinity. This approaches Right, because this is too small. You don't even care. Even if a is negative, it doesn't matter. This overtakes this, no matter what. So this approaches infinity, no matter what a is. What about this? What does this approach? Definitely infinity. And this is our second indeterminate case. Yes, no one knows what to expect. And we cannot draw conclusions. That's our second one. Infinity minus infinity. Anything can happen. That's why it's called indeterminate. Okay, so I'm coming back to, that's our second case. I'm coming back to the problem, and you will tell me what to do. Infinity minus infinity is an indeterminate case. Look at the function and say, oh, I know, and tell me what to do. You can skip that part, but just tell me what to do. We've done this. I can't. Say it again. Rationalize. Thank you. Exactly. We don't have to think. Well, we do have to think, but you know what I mean. Okay, excellent. When I see a radical and I see something like this, that's my first thought, of course. Thank you, Brian. Okay, so can anyone dictate? The square root of
plus ax minus or plus square root of
very good. And the same thing in the denominator. Good. Good. Next. What is the next step?
x squared plus ax minus x squared minus b.
Excellent. Over the denominator. Very good. Perfect step. Next. Yes. Awesome. Next. The two terms from the top have something in common. What is left? Good. Now in the denominator, I do have to factor, as Thomas said. He said at some point in time, factor out x squared. I have to do that now. Okay. But here's how we do it. Look at this polynomial and tell me its degree. 2. I will have to factor out x squared under the radical in both cases. But now whatever I'm going to put in parentheses, it has to work. So I cannot just put 5 and 3, right? Whatever, that was a silly example. I have to put whatever such that x squared times this is this, and x squared times this is this. Definitely 1, and definitely plus a over x. Let's check and make sure that this is clear to everyone. Is x squared times 1 x squared? Is x squared over 1 times a over x ax? One more time. X squared over 1 times a over x. I simplify and I get ax. Perfect. We repeat in the same way for the second one. What do I have in parentheses in the second one?
1 plus b over x.
Very good. Indeed, 1 plus b over x. Perfect. Next.
So now you can just break the square root.
Exactly. I can break it. See, as Thomas said, he said, break the square root. True, but I have to be careful. I have to be careful. So here's a note for you. The square root of x squared is the absolute value of x, which can be x if x is greater than or equal to 0, or it can be negative x if x is less than 0. If this is negative infinity, then I have to use this. Since this is positive infinity, I will use this. But you have to be very careful. You cannot assume that you are taking out an x. It could be negative x. In this case, we're safe. I'm not going to have to use this because I have approaches infinity. When approaches infinity, it cannot be negative. Okay, so then, yes, we are breaking up the radical. And then my next step would be limit. I know, it's a long problem. A minus b, stay with me, please. We're almost there. So then this is x, the square root of 1 plus a over x, plus x, the square root of 1 plus b over x. Yes! Factor out the x. Excellent. From the denominator. So I have limit, as x approaches infinity, a minus b over x. And what is left in bracket? I use brackets just because, just for everyone to see. You can use parentheses, it's the same thing. Square root of 1 plus a over x plus the square root of 1 plus b over x. Perfect. Of course, that was the whole trick. That's why I already factored it out from the top.
Because x approaches infinity, so it'll be 2 at the bottom.
Exactly, exactly. Perfect. So now careful. Notice one thing before we finish it. The limit operator did not go anywhere yet. So please be very careful. I cannot drop the limit operator. Now I can at this stage. At this point in time, I will say this approaches 0 and this approaches 0 because it's a number over infinity. Because it's a number over infinity. This is what where's my handout? Did I put it here already? I think so. Yes, I did. Okay, this is what we said. A number over infinity. A number over infinity when x approaches infinity, 0. When x approaches negative infinity, a number over infinity, 0. So then these two are 0. The numerator is a minus b. And the square root of 1 is 1. The square root of 1 is 1. 1 plus 1 is 2. Now, these are all numbers, a and b. The limit of a function is a number when x approaches infinity. What do we conclude? Therefore what? Y equals
A
is
horizontal.
at infinity only. I have not checked what happens at negative infinity. I don't even know if it exists or it has a limit. I haven't checked anything. We have 10 more minutes. I'd like to choose another limit, please. Anything you want. The last two sections go together, and I cannot rush more than it's a lot to explain. It's a lot to go through. Okay, so let's choose. Any preference, or I will choose. Any preference? Okay, I would like to look at problem 42 on 141. Very important type of problem. Find the horizontal and vertical asymptotes of each curve. If you have a graphing device, check your work, la la la. Okay, so I have y equals x squared plus 1 over 2x squared minus 3x minus 2. We're asked to investigate all possible asymptotes that this function can have. It's a rational function. Obviously, it can have horizontal and it can have vertical asymptotes. Okay. When will a rational function have vertical asymptotes? When
X
when the denominator equals 0. When the function is undefined, in other words. So then 2x squared minus 3x minus 2 equals 0. We can factor or use the quadratic formula. What would you prefer? Okay, so 2 times negative 2 is negative 4. We want to find, because this is not 1, I have to get it involved in the problem. And the sum is negative 3. So I'm looking for two numbers whose product is negative 4 and whose sum is negative 3. Do they exist? Yes, negative 4 and 1. The product is negative 4. The sum is negative 3. Now I will rearrange the whole thing and change negative 3x into negative 4x plus 1, the two numbers that I just found. You can use the quadratic formula if you, or any other method of factoring. It's up to you. Okay, I always use my whiteout to do this. Okay, so we have 4 terms. I will factor by grouping 2x and x minus 2, and I have to get an x minus 2 from the other two before I even look. And yes, it's there. So then the factor form is x minus 2 and 2x plus 1. I accept any method, quadratic formula or otherwise. Okay, so what are the potential vertical asymptotes? And I'm saying potential because I'm not sure if you remember, since is this factorable? Is x squared plus 1 factorable? It's the sum of squares. Sum of squares not factorable. So there is no way, so this function becomes x squared plus 1 over x minus 2 x plus 1 half, right? So there is no factor to be simplified, because if there is a factor that I will simplify, like if x plus 1 half goes away or x minus 2 goes away with something from the top, those will not be vertical asymptotes. They will be what? Hole in the graph. But since no factor from the denominator disappears, I know for sure that x equals 2 will be a vertical asymptote, as x equals negative 1 half is a vertical asymptote. But this is not sufficient. I have to show the limits. I have to find the limit as x approaches 2 from the left, from x squared plus 1 over x minus 2 x plus 1 half is what? In a moment. I have to find the limit as x approaches 2 from the right, from x squared plus 1 over x minus 2 x plus 1 half. I have to show, oh, I really meant to write 2x plus 1. I didn't need that. 2x plus 1. It's good enough. That's a factor form. These are the solutions. The vertical asymptotes. Okay, so I'll find that. And then I have limit as x approaches negative 1 half from the left of x squared plus 1 over x minus 2 2x plus 1. And the last one, limit as x approaches negative 1 half from the right of x squared plus 1 over x minus 2 2x plus 1. Yes, I know this. It's clear. Those must be vertical asymptotes. However, I have to determine the accompanying limits. Okay, so let's do 2 from the left. Yes, the top is positive no matter what. So I don't have any worries about the top. But what about this? 2 from the left, which means 1.9. Negative, positive. What is the limit? 2 from the right, 2.1. Positive, positive. Limit. Negative 1/2 from the left, which is negative 0.5, right? Let's say negative 0.6. Negative, negative 0.6 is negative, right? So it's positive. Very good. And with negative 0.4, negative but positive. Limit. So I know I have 3 minutes left. So I determine the vertical asymptotes. Now, how do I determine the horizontal asymptotes of such a function? Exactly. I have to find the limit as x approaches infinity from x squared plus 1. And now I don't want the factored form. I wanted the factored form for the vertical asymptotes. So 2x squared minus 3x minus 2. Okay. Here's how we approach this now, which we did in pre-calculus this, but not using this limit operator. So what is the degree of the top? I'm going to factor out 2, x squared. What is the degree of the bottom? I'm going to factor out x squared. Please tell me what is left inside. Very good. What about the bottom? Yes? Minus 3 over x minus. Very good. What happens to x squared in front? What happens to this when x approaches infinity? What happens to this when x approaches infinity? What happens to this when x approaches infinity? What happens to the whole thing as x approaches infinity? That's it. Which we knew from pre-calc. The leading coefficient of the top over the leading coefficient from the bottom if they have the same degree. So then y equals 1/2. No, there is not going to be any change when x approaches negative infinity. So y equals 1/2 is what? I just have to show, but it's not. I have not used the fact that the x approaches infinity in the sense of the sign. This is 0, 0, 0. It will be the same when negative infinity is in there.